You know how a bicycle works. There are two wheels, a frame, pedals, and if you push them, the wheel rotates and there it goes. This is enough to describe the concept, but you also know there's more to that. You want to turn to stay on the road, you want to switch gears to adapt your power and speed, brake when you want to stop, and a helmet is highly recommended for safety.
My name is Mascaron. I'm a cyclist and a nuclear engineer, and I will pitch my Gen 4 PhD research carried out at CEA in France. I studied molten salt reactors, which are nuclear reactors with fuel in the form of a hot liquid, circulated from the core where fissions generate heat to heat exchangers. The heat is then carried by a coolant salt and used to generate electricity in a power conversion cycle. This is the concept, but as with bicycles, we must figure out how to operate MSRs, a topic rarely covered in literature. In my PhD, I propose a methodology to define and assess strategies to control MSRs depending on their design.
For instance, when to brake, how much, with what brake technology, and how do the answers to these questions depend on the bike design and on the road you follow.
Let's take Aramis, a chloride salt MSR at nominal power. Now, assume we want to operate at 50% power, without using control roads or adjusting pump speed. Applying a lumped parameter static model I developed, we obtain a new steady state. Globally, the temperature rose, except in the fuel hot leg. Due to important temperature variations, I used my model the other way around. This time, I want the cold leg temperatures constant. To make it work, I must use control roads and adjust the coolant pump speed. More generally, we can compute the operating temperatures depending on power and the corresponding commands. These altogether define a control strategy.
And in case of an accident?
I performed safety studies. With a time-dependent, one-dimensional model, I extended. For instance, in a reactivity insertion accident, the fuel temperature reaches a peak before stabilization thanks to reactivity feedbacks. With sensitivity analysis, I derived an analytical correlation to predict this peak value from reactor parameters and their operating conditions that depend on a control strategy. In other words, I propose an approach to assess the safety of a MSR in various operating conditions and to improve it by adapting its design or the control strategy.
Let's hope that my research will help MSR designers going to the right direction from the starting line. That's all for today. And now, time to hit the road!